So on the right side of your screen, you have a chat area where you can ask some questions that will be taken into consideration at the end of the webinar. So please write any question you want, and do not forget to click on the bubble with the interrogation point inside before validating your question. And if you do that, we will be able to answer it directly at the end of the webinar. Okay, so the title of this webinar is Specific Dynamic Characterization of High-Strength Steel for Triaxiality Damage Model Calibration. This webinar will be presented by Jérôme, my colleague, which is here. Jérôme is responsible of doing some numerical simulation, material model calibration, impact experiment, and so on in our lab for almost 20 years, and it will present you this webinar. So the main outline of this presentation is some explanation of some defense application of the methodology we are going to present in this webinar. Some information about high-strength steel, and also we will take time to develop a methodology which is called the BBA, so the building block approach. We will detail this methodology, and we'll apply it on high-strength steel. Just a short slide on about THIOT. So THIOT has two main core activities. The first one is the design, the manufacture, and the delivery of test equipment related to shock physics studies. So we've been doing this activity for more than 34 years. About this kind of test equipment, we are able to manufacture some laboratory launchers, so single stage gas gun or powder gun, double stage gas gun or powder gun, split Hopkinson bar, acceleration generators and detonation chambers, and high pressure equipment, so detonation chamber. The other activity is mainly dedicated to services, expertise on dynamic phenomena. So we have for that a shock physics laboratory that has opened in 2008, where we can use our test equipment, so gas gun, acceleration generator, split Hopkinson bars, to investigate the impact and dynamic behavior of material. And this kind of equipment can be coupled with our ability to perform some numerical simulation with different FEA codes. And with that, we are able to expertise some dynamic phenomena and to answer to some research and development projects that are related to material behavior. And a new activity that has been started, the first training session was back in 2019, only one session, then we had the COVID. And now for about 1 year and a half, we have started to make some regular training session on different topics. The first one is introduction to shock physics, and the second one is more dedicated to a ballistic event, and I will present it to you at the end of this webinar. And now I will let Jérôme present you this webinar. Jérôme, please.
Thank you, Paul. So welcome everybody. So short introduction to different defense applications we deal with in our company, but perhaps you can be face off in your own entities. So if you look on the threats in terms of increasing energy, can impact on blast or acceleration. So it starts from soldiers that can have damage, or they surrender some threats. It is the lowest level of threat energy. And after you have aircraft, missiles, and space applications. And you see, I only present some example on some impact we have realized in our short physics labs. After you have tactical and light armored vehicles, so you increase in terms of velocity, in terms of mass projected, so as to damage, to stop, or to design some protection of our vehicles. And the last energy, highest energy we can consider now, they are on building and infrastructures. And so you have an example with on the top on a self-forging projectile with explosive, at the bottom some numerical simulation we have done in our laboratories for concrete penetration with a kinetic energy penetrator. So today we're going to more focus on tactical and light armor vehicles and on steels. So if you consider a tactical or lightweight armor vehicle, you have various kind of threats. You can have conventional or ammunition and improvised explosive devices, IED. You have some picture of example on glass panels, so you can have some fragments. On the side of the vehicles, you can have warheads with multi-fragments that can hit the side of the vehicles. Example of some simulation we have done, and some multiple fragments we have done in our laboratory to represent in a laboratory condition with good diagnostics the impact of single or multiple fragment. And to finish, I will show you some example of what happened to air blast and buried charge. On the left, you see what happens to Hummer with a 3 kilogram TNT below. And so you see it's completely destroyed, and people for and you take a vehicle that is already dedicated for military application. So you have some solutions to for the same threats to have some protection below to damp the energy, and so to allow after to exit in fact the zone and to protect the soldier during this huge event. So in dynamics, we speak about strain weights. And if you consider roughly all those applications for tactical and lightweight armor vehicle, so in terms of strain weight, if you consider the blast for the soldier inside, you have strain weight needs times for deformation to occurs. You are roughly below 100 per seconds for soldiers. If you consider the blast for the underbelly explosion on the side can go up to 10 power 3, and if you look on impact, you are higher than 10 power 4. So on all this range of strain weight, people considered and are still considering some high strength steels, and they are widely used as a structure or as armor materials for those vehicles. In terms of impact conditions, you can see on the influence of these impact conditions on impactor behavior and target response. This depends on some parameters. On this picture, you can see what happens if you have on the left column some low ductility materials, on the right with high ductility materials, and depending on the condition, you can have from the first row some small fractures at the back of the armor. It is called the behind armor damage that can happen inside vehicles. If material is a high ductility, we are more telling in the frontal side of the panel. Depending on the dimension and the materials, you can have some plugging, some shearing appear here, and some petaling at the rear rod if you have ductile materials. And you can also have some radial fractures or a ductile or enlargement if you have a ductile material. So depending on the condition and the material for the impactor and for the target, for the steel protection, you can have various scenarios of impact and so various response you have to consider. An example from the literatures from Borvik and colleague in 2002. They consider the same weight of projectile, but with different noses, a flat one, hemispherical noses, and a conical one. And as you can see, the shape of the hole and the penetration is not the same, and so the energy also is not the same. That is stopped by the plate, and so it means that the geometry and the stress and strain condition during the impact at the beginning and during the impact can condition how you may stop or not the projectile that is hitting the target. And this is an extreme case when velocity increases. It is more for an example in terms of hypervelocity impact. You see an example of a very large target. You see the impactor, it is a small sphere you can see in the hole. And as you can see, you have no penetration. In fact, the hole is only less than half the thickness of the very large target, but at the back, you have a big opening that is really close to have a small fracture behind the target. So it means that even if you have no penetration, you can have damage behind the armor. And so if you have some soldier behind this armor, if you look outside, there is no damage, we see no hole, so we have no risk for the soldiers to be injured. But in fact, if you have a small back face effect, it can hurt soldiers. I know the armor, in fact, don't make its job. Some short graph about steels and their evolutions. You will see what we call usually the banana curves for steels. You have the ultimate strength on the horizontal axis and total elongation on the vertical axis. And years after years, people try to increase the product ultimate strength multiplied by total elongation, because the more this coefficient is important, the more you can damp the energy, or you have the capabilities to damp or stop an impact, for example. So at the beginning, people start with some mid steels, and after some conventional high strength steel. And to do those high strength steels, they start to change and master the change of the various phases inside those steels, the composition and how they are formed and where. And people years after years use various kind of techniques, and they stop to call them high strength seals. They start to call them advanced high strength seals, and they use the various different process to increase this capacity. They double, you see, from 10,000 to 20. And in the roughly in the I think the middle of the 80s, people managed to triple to multiply by 6 the value they were beginning. So they reach 60,000 with material like with twinning-induced plasticity phenomena. But they managed to make very high quality and very performance steels. But at those moments, they managed to did them, but in terms of cost, in terms of industrial production, they were too costly. So they changed the objective, and so there appears some that it goes the third generation of advanced high strength steels. So they diminish a little bit this product, but they managed to make them realistic from an industrial point of view. So you see, and people continue to develop steels and some way to produce them to have the good compromise between price, production plant also to be able to do them, and capabilities of those steel. So if we speak about the materials, in fact, structural and high strength steels are worldwide used in if you look outside the defense application in transport and civil engineering. Their mechanical properties range from 200 and 2000 MPa in terms of yield strength. In quasi-static, you have some example on structural steel on the left, from very normal strength steel at the bottom and high strength steel on the top. But these values are in quasi-static. But as soon as you include dynamic in the effect, what you can see, if you compare this graph on the bottom right, show you the dynamic increase of the dynamic effect on the steels, and you have at the bottom the strain weight increasing. On the right, this dynamic ratio. It means that if you have a value of 2, it means that the yield stress in dynamic at this value is double at this strain weight compared to the caustic one. And what you can see is that for the low carbon steels you have at the bottom on the left curves, they are on black on those curves. They have high abilities to increase in dynamics compared, for example, to micro-alloyed steels in blue that are higher in quasi-static, but they are less effect in dynamic. So it shows that depending on the strain weight and the condition where the steel will be employed, sometimes it can be more effective from economic point of view to select a steel that is a little bit effective in quasi-static, but have more capability to respond in dynamics. That's why dynamics is very important if you consider, in our case, some defense application. So we need we propose a building block approach strategy to characterize the materials in the good regime in terms of stress, strain weight, temperature, etc. So you want to make this part, or okay? So in terms of strategy, we combine in our shock physics laboratory, in our team, a complex expertise in dynamic phenomena, and we have a case study. It can be bird impact or some application for space research or in ballistics. So we have the case study, and so we make some state-of-art experience on what was done in this specific case study or with the materials that are employed in this case. Also, we investigate theoretical models and material science to check what model can be good in this case of application or not. We make some numerical simulation. We have various explicit codes, and we use different of them depending on the application. But also we make also some tune experimental means and diagnostics. We use them to collect some data to feed the strength models. After they are fed to numerical simulations, and so we have all those steps together to respond to the case study that is given to us. So as I mentioned before, it is a continuous dialogue between experiment and simulation to make design more reliable. So on the left, you will see the experimental works, on the right, the numerical simulations. So we start with the structures or the subsystems we have to design for our customers. So we first make a phenomenological studies, and after we make on classical specimen some quasi-static dynamic test, so as to collect some data on elasticity, plasticity, strain weight, and some damage. And then we make some coupon to make some dynamic test and to adjust the model. And after we can have another steps that use some components. It is not the full structures. We will not test, for example, here a complete tactical vehicle, but for example, we can test a door, a part of the door, or a subsystem, and so we can make some model validation in simulation and compare them to some impact test to show that you have good correlation of the material models. And all those steps, by making together experiment and simulations, and to make a continuous dialogue between them, we can ensure good representation of what will happen to the structures after. So on the various steps, some words about the phenomenological studies. So to determine the structure strain, stress, and strain weight regime. So we take the 4 points I detailed before. We make the preliminary study by ourselves, or the customers give us some data, and those data are typically the type of deformation. It is elastic, plastic, up to ruptures. Is the response isotropic or orthotropic? Depends on the material, of course. In terms of temperature range, negative or at very high temperatures for for motor, for examples. We have made some studies in high temperatures. In terms of low stress levels, 100 MPa or over than 2 GPa. And in terms of strain weight, between intermediate strain weight 10 to 20 and up to 2 or 4,000. We need this data, in fact, to make the good test and to select also the good simulation models, numerical models. So steps 2 and sometimes 3 if we want to adjust, we select the most relevant material laws for available simulations. So the laws normally in explicit codes, we have 3 main laws or main equation or models. The first one is the equation of states that defines the pressure in function of the specific volume of temperatures. More generally, if you take a cube of these materials, the more you press the cubes, the more it's hard to press. Equation of state, example for steels, the Young modulus, it's only elasticity, is the only information sometimes you need to define the equation of state. For the strength models, you define what we call the deviatory stress. And this deviatory stress is function of plasticity and strain weight. So if you take samples, you pull it, and the more it plastifies, the more the stress. And the last models are the damage and rupture models. So damage and rupture models can be defined on maximum strains, can be triaxiality dependent, or you can have some stochastics also in the models. And in fact, this part of the model is used way beyond what the material can surrender. So you see there is 3 laws, 3 kinds of laws, so we have to fill them, all of them, or some of them, depending on what we have to simulate and to help in design for our customers. So if we come back to the high strength steel and about the strength models, so what we're gonna present, this study was done for our customers. He give us some authorization to present some data, but he asked us first to look for Johnson-Cook model. And if you look on classical Johnson-Cook model, so the question is here. And this model, in fact, that defines the deviatory stress, it is a multiplicative models. You see there are some parentheses, and there are three parts. First one defines the yielding, the second one the strain weight effect, and the third one the thermal softening. So in fact, if you look at the models, you have only 5 constants, A, B, N, C, and M, and these 5 constants in this model defines strengths in this model. So it is one of the most worldwide used in a thermoviscoplastic model, but it is with monotonic evolutions. It means the evolution is continuous. So in this case, so our customer asks us, okay, we want to use the tabulated Johnson-Cook model in LIS Dyna. So instead of 5 constant for strength model definitions, the model is defined with 2 sets of curves that defines 3D surfaces with stress versus effective plastic strains, function of strain weight and temperatures. So you enter some curves. If here we look on the strain weight, you see you have the strain weight are defined by various curves, and each curve is given for a specific strain weight. And after, you make also some tests that can be done in quasi-static and preferably in quasi-static, in room temperatures, in negative, and in high temperatures. And so it will define some curves with the thermal softening, and you get various set of curves that define 3D surfaces, and so the strength model will travel depending on the condition on those various curves. In terms of ruptures and damage model, so this model, we have to have a look on the stress state regime, and we speak about triaxiality and load angle. So there are 2 strange words or some terrific words for some of us, but in fact, it's only a change of coordinates or system coordinate system. In fact, if you look on the geometry, you have the stress in X, Y, and Z. It is a Cartesian in Cartesian coordinates, and after usually mechanical works in principal stress directions, and there are direction 1, direction 2, and direction 3. And in fact, when you call about triaxiality and load angle, we change the model, and it is like cylindrical models. It is defined by the pressure, the triaxiality, and the load angle. It is called the A. Westergaard model. Thank you. So we speak about triaxiality because the triaxiality will enter in the definition of the plastic failure strain. If you look on this graph, you see on the abscissa the compression, the triaxiality. We have some indication between minus 2/3 in the compression direction and plus 2/3 in the tension on the right, and you have the value of the plastic failure strain. So you can have a model with a constant effective plastic failure strain. The model can be constant. If you take the Johnson-Cook failure model, you have, if you look on the triaxiality, you can define the curve that is like this with an exponential, and so you have two constant, but some materials have an evolution that is not monotonic, and they can vary. You can have various waves in this shape, and so the plastic failure strains can depend on the triaxiality, but also it can depend on the load angle. So so it can be not only represented by an exponential. And to get access to these variations, people have to do many tests, and depending on the area we are looking for. If we are very the stress regime is in very small windows in terms of triaxiality or load angle. For example, if based on the phenomenological studies, you see that your material will works in this area, you need to perform and to be well calibrated for this model in this area. You only need some kind of test. But if you need the whole behavior in all the states in terms of load angle and triaxiality, it means that you have to make various kind of tests in all the regions to ensure correlation of the model. For example, if you look here, to get access of the failure in this region, mean with load angle parameter equal to 1, and with a triaxiality level between 0.4 up to 0.7, you need to make such kind of cylindrical tensile test, and by changing the groove, you will change the triaxiality inside the samples and to get access to various points here to get the failure strain. So, in fact, yielding up to rupture define you 3D surfaces of the failure stress depending on the triaxiality and the load angle. So, if we come back to the Johnson-Cook classical models, so you see you have the triaxiality here, you have the strain rate, and the thermal softening. So here again you have 5 constants. We only speak before with the triaxiality, but also you have the strain rate and the thermal softening. And they are still monotonic in terms of evolution function of the triaxiality. But as you can see here, you have only the exponential, and so you cannot represent such a rupture in the model. So it cannot represent such kind of response. And to face this lack, the tabulated Johnson-Cook model that was developed, so instead of getting 5 constants, you have the failure strain here, and by making all the tests I presented before, you define in terms of the stress state, the failure strain, function of the triaxiality and the load angle, but also, and as soon as you get this 3D plastic strain failure surface, you multiplied it by 3 functions to take into account the dependency of temperatures, the dependency of the strain weight, but also it is included the dependency of the element size. It means if you have very fine mesh like this for some tensile example at 0.25 with more than 1 million element to only represent the samples, you can get and have the same failure strength with multiplied by 4 the size of the elements, but to only 7,500 elements and to get the same failure strength. So this model allow you to regularize, in fact, your failure. So now we're gonna show you what we apply the BBA to these material models. So we don't calibrate to all the maps in terms of load angle and triaxiality, but we focus on some tests. So we have made some standard quasi-statistics, but these I will only present the complex test in mixed configuration in terms of triaxiality and strain weight. So we have performed some dynamic high tensile tests in our company. So we have some special test bench, but also we have made some plate sample in dynamic tests with DIC, and so we compare every time the various tests you can see on the various curves and in red the simulations. Here you have the strain comparison at the middle of the sample is here comparison between what was measured and given by the DIC here with the free test, and here you have the simulation up to the fractures to show that you have the same evolutions, and we follow the curves with all the tests together to fit the models. Here we have another examples on the cylindrical tensile Hopkinson bar test with tracking. Here you have the stress versus strain, but here you have some tracking on some dedicated point to follow that you have the good necking here and the good evolution of the tensile here. So this is a part from step 2, in fact, in the BBA strategy, to collect the data and to fix the various curves of the models. And what we did, we make to validate those models. We have performed some impact test with heavy projectiles with on a heavy clamped plate of the materials. Here you see the heavy projectiles. They have all the same, roughly the same weight, and they have 3 different noses that was presented before with the literatures. So you have the gas gun here. You take the velocity, 3 different noses. We have some clamps. We clamp the plate, and we have set up a high-speed camera. We have high-speed cameras to measure the 3D deformation of the plate at the back. And as you can see, we have performed 2 kinds of tests. One at the beginning of the failure, at the failure initiation. You see here as an example with the hemispherical head. And also we have made some complete perforation, and here you have the example with the conical nose projectile. So we have compared those DIC measurement, and when we have complete penetration and residual velocity, we have compared the velocity. And you have here a table which summarizes the results. And you have comparison for the various shape here on the various line. The consumed kinetic energy, the residual divided by the initial incoming kinetic energy. Here you have this ratio in terms of what we get from testing. And here you have the simulations, and you see the discrepancy between the test and the simulation is less than 5% between the test and simulation. It means that the BBA used to correlate the material strength and damage triaxiality dependent model was good enough, and a very good representation on what happened after with some case studies. That represent different impact scenarios with various triaxiality on the plate, and we get very good results, and customers was happy of this. So in terms of conclusion, so we investigate the dynamic behavior of iso and steel in our shock physics lab. We've tuned a limited number of experiments, and they're optimized using LS Dyna. we have shown very good model calibration of this material model in Arizona, the tabulated Johnson-Cook model with triaxiality effect. And we make it using this building block approach to minimize the number of tests and to optimize the coloration after. And we have performed some validation tests using well-adjusted diagnostic tools. And it is very important to have good data to compare after with the simulations. And those comparisons have shown that we have very good agreement of the material law. So some key points to keep in mind. This strategy we use can be applied for various kinds of materials. It allows tuned material behavior calibration, but also can be used for complex strengths and gyro model that have to be selected in function of the stress state and failure modes observed experimentally. And some investigation can do numerically. But the most important is that the strength and damage model have to be calibrated in the good stress state regime in accordance with the final application in terms of triaxiality, strain weight, and temperatures. And to know more about the ballistic response of metals, perhaps Paul, you want to continue?
Thank you, Jérôme, for this presentation. Following this topic, we have the next training session that will occur in November, so 1 month from here. It is entitled Ballistic Impact on Protection Steels Test and Numerical Modeling with Embedded IFEA. In fact, we will develop the main challenges that has to be tackled when you perform some numerical simulation and you want them to be as reliable as possible. So it will be described like presented here. So we will have a short presentation of the main challenges of ballistic simulation of impact events. We will present you also some description of the impetus IFEL solver with an introduction to fast dynamics and to ballistic simulation. You will be able also to have some introduction to experimental techniques with simple stage gas gun, split Hopkinson bar. You will also be able to manipulate some high-speed camera, DIC, and so on. And of course, we'll have some impact testing in our lab. The impact test we will perform will be a spalling test, as Jérôme presented in the beginning of this presentation. And we will also focus on the different other aspects, which are perforation, plugging by adiabatic shear bonds. And for each of these case studies, we will develop some numerical simulation and numerical tools adapted to perform this simulation, and also the adapted experimental techniques to calibrate these material models. And at the end, we'll do some calibration process and compare the result of the experiment and the numerical simulations for these 3 main cases. So this next session will be in November. We will still have some places, and we will share also the schedule for the planning for the next year. It's planned to have three different sessions. So this one will be reconducted. We'll also have a session on the introduction of shock physics and another session for the diagnostic tools, so measurement techniques adapted to shock physics and impact testing. And I think that's the end of this webinar. If you have any question, please do not hesitate to write them into the chat area. We have so far 1 question, and we can try to answer.
Okay. Can we measure the pressure during the impact generated by a projectile? Yes, it is possible, but it depends on the projectile and the configuration. In fact, this test can roughly not be done with a classical impactor, because if you put something inside to measure, you can change the way the impactor will react. But you can have some configurations that can help you in getting this information. But also the gauges and the conditioners for this kind of measurement are not, can say, classical, because they are inside the target, and so the way you put them in the target also are, can say, critical to implement. So people have done some experiment, but you're not a lot of laboratories I did it. In fact, the people get some information about this by making indirect correlation using the simulation codes. You have the global response, or you have some points, and so when you get those information by post-treating your models, and you correlate it, getting some information from outside of the target. Can be IC or some PDVs in local point, or sometimes some X-ray pictures inside the target. And so you have the position of the projectile and its deformation all along the penetration. And so when your simulation reproduce all the events you get from those diagnostic means, it means that you will decelerate penetrator, or you get roughly the good behavior. And so those data is given by the simulation.
Okay, we have another question.
Yes. Do you make the same BBA strategy for hypercity impact regarding strong weight? Oh, this is a huge question. Until now, we don't have a huge study using BBA in hypercity. This can be done, but people who need it or wanted to do it, because the conditions are very high, the number of tests would be different, and so the configuration will be more complex. It is not impossible, but the budget are the same than making those kind of BBA strategy for, say, ballistic or aeronautic event or something like this. But it's not impossible. It's only a question of cost and sometimes time, but we are open to any kind of such a project, of course.
Yeah, this could be applied. The main problem with hypervelocity impact is that if we want to develop some specific characterization techniques to evaluate the behavior of material at this level of strain rate, it will be extremely costly. So what is mainly done so far is using numerical simulation and performing some, let's say, extrapolation of behavior from behavior at lower strain rates, and then we'll try to correlate our numerical simulation with hypervelocity impact events, and adjust, calibrate our model to fit as best as possible the simulation. Another question.
Does the equation of state of the material target affect fracture type in any way? Not always, because if you have for some targets like some porous one or some concrete or other, you can have some equation of. It depends on the velocity. If you have in a total, you have that effect, and in some models, the more you stress, you can change the way the fracture happens. So depends on how far you go in the simulation or in the experiment you do. It's clear. Open to your questions.
We don't have any question.
To my opinion, not for diversity impact event, because in hypercity impact events, in fact, the deviatory stress has a very less effect, and you are more dependent on the equation of state instead of the strength part of the model. The impact, but after the impact, if you have the structures after, the strain rate diminish, the stress diminish the pressure, and so perhaps this model can be used outside the impact, but in the impact zone directly. You can spend a lot of time, a lot of money to characterize this model, but this is not where the key is for the response directly to the impact. Because when we speak about hypervelocity event, we speak highest value we take still for roughly the velocity. It means 5 or 6 kilometers per second, and that is speed. Strength models, you can put something, but at impact zone, they react roughly more than fluid than wheel solid. Okay, just go back to the
we haven't an additional question, but it cannot be published because
I have to find the good. It is a question about the temperature effect in DMX test with a resistor. I think it is not in this part of the presentation on the high strength model, but perhaps it is more on the beginning of the. We go back. It is roughly in the second or. Back. Okay, so what precaution should be taken during this dynamic test with temperatures, high temperature or low temperatures? We have no specific precautions. In fact, when you do this test at room temperature initially, you have an adiabatic heating of the target, so it increases. So you have to take into account when you make dynamic test in room temperatures. But I think after another one of slides, you have a resistor that is placed right next to the specimen, and then there is debris touching the resistor. Okay. In this, I will try to go to the first slide. In this case, here, I think this is one. In fact, this can be considered as a validation test and not as a characterization test. The way the context of this study was to, you can answer Paul if you want. It is an impact on a material that is subjected to very, very high temperature. We speak about 1000 degrees Celsius. And so this validation test was, they only ask us to make this impact test at very high temperatures. So we have like, you see some inductive heating coils. And so you see a picture on the right of the target just heated. And you see we launch some metallic sphere, and they pass through the coil. And after, when we get the good temperature, we have some various thermal couple to get access to this, to see if the temperature is homogeneous. And so we make the validation test. But we didn't make, in this case, some characterization of the behavior of the materials using classical samples in high temperatures. That's something you can complete. But,
yeah,
that's something you can do.
This test was only a validation test, I said, Jérôme, but of course we can apply the BBA approach to characterize this material at different levels of temperature. So the temperature effect can either be investigated in quasi-static regime or also in dynamic regime on speed looping on bar, for instance. And I'm not sure about what is the reason for the question. What precaution should we take? I think it's experimentally speaking. Sorry. So yeah, if you want to correctly use the result of this impact testing, you have to ensure that the temperature field is quite homogeneous all over the impact area. So for this application, the inductive coil was especially designed for heating this material at this specific temperature. So we had to use a very specific power generator, a number of coil that is also adapted to this application, and also the distance between the inductive coil and the target was also critical to ensure that the around the impact area, the temperature was as homogeneous as possible.
Just to see on the, if you see on the videos, on the video that is shown, so you see it's a very high temperatures. I will not say what kind of material it is, but you see there is like still a fragile behavior. You have a big stick, big piece part, and you not have like a ductile material even if it is high temperature. So characterization can be done in high temperature or in low temperatures. We have to take care on the test bench, but also on the various diagnostics you put all around to get access to the information you want to collect.
Okay. Question: for establishing the parameters of any material model, maximum characterization is done in tensile mode. For isotropic material, so does this parameter will change if compression testing is used?
So in fact, normally in compression you have no ruptures. Ruptures come shear, and the shear you got it in tensile. It happens, but in compression normally you cannot define some rupture in compression. If you take, I show a cube. If you have a perfect compression of specimens, if you have some ruptures, it comes from the applying area. From the shapes, you generate some cones, some adiabatic shear bands, but it comes because you have a shear. It is not a pure compression. That's why people, it is more easier to get access to the failure in tensile configuration instead of compression.
Yeah, in fact, it depends on what your material will exhibit. If you are only interested in calibrating a material model, without failure, then you should consider to characterize it under compression loadings. But if you want to calibrate a material model and a failure model, then you will have to consider performing some testing, some tensile experiments, and if your material will exhibit also different triaxiality levels, then you will have to change and combine the modes, tension with shear or compression with shear, and evaluate the effect of this loading on the failure strain. Sorry. Okay. think there is no question.
Just to wake up everybody.
Okay, so if there are no other question, then I think we should stop this webinar. Thank you, Jérôme.
You're welcome.
Thank you everybody for attending again this webinar. Stay tuned for the next webinar that will be organized by the end of the year. And if you are interested in any information, please do not hesitate to contact us
or to the next
for anything,
or for the next
training sessions, webinar, or if you have any question that raises following this webinar, so don't hesitate to contact us. Thank you, everybody. Thank you, Jérôme. And
welcome. And there are still some place for the next training in November for the ballistic and metals. So if you are interested, don't hesitate to ask.
Thank you all. All right.
Bye-bye.